6, 7, 8, 10. Вот это количество имен. Это количество решений даже. Это количество решений. Это есть там. А вот это их бессмысленно. Мы знаем, что произведение, значит, знаем, что эти каждый твердый все. Находим висящую вершину, выкидываем. Подняли висящую вершину.
Не,
Нет, слушай, я люблю электрические доски.
Хорошо.
Да.
Слушай, я сейчас просто брошу вещи наверх.
Да, ну тут народу пока 3,5 человека.
3,5 человек.
Не знаю. Нет, ну ладно, решили.
Мне показалось, что есть. Возможно, что, например, скорее
Ты здесь не был. Я здесь никогда прошлого года не была. Просто учебного года, блин, да. Не знаю.
Ну, это типа совсем много.
Очень нравится. Очень нравится.
Да, там получается.
У меня сейчас
Привет. Нормально. Нет,
даже вас может запишусь, потому что просто
да, нет,
не
все понял. Я здесь. Ну, я в лаборатории. Ну так. Прекрасно, работа, никто ничего не делаю, платит обязательства еще. А вообще учу детей на 43. Да. Я просто не могу
Да, там половину или еще максимум 5. И ПГ. Третий это 3 задачи. 5, 4, 2, 1. На самой Питерской 6, я вызвала 4 часа, у нас было 2,5. И у меня было 8 задач, это скрещенный был вариант. Так что я считаю, много результатов. Но, конечно, я взяла одну целиком и дополнила с середнячком на стопку. Так что в целом, ну, конечно, количество очень ну, так и должно быть, да. Надо ее попробовать к празднику. Его нужно вообще не кушать. Зачем мне лучше важно? Поставлю кого? Зачем?
Если нет денег.
Ну, это в конце года лучше. У тебя уже есть, да? Скинь мне фобию, да? А это оно лопнется? Уверен. Наверное.
У нас как-то стало больше. Так, и что? Где здесь нажимать?
Ну, не знаю, какой-то студии в поле не было. Вот там, наверное, да.
Это прямо слово лекция. Сколько? Так. Чудовищно. Ну вот, я же говорю, что это какой-то...
Да, ну, школе лучше.
У вас в школе шикарная доска. Я знаю, какая доска у вас в школе.
А, тут какие-то извращения.
Какие-то, да, какие-то глупости. Так, как я с вами? Сейчас. Нет, не трудно. Я хочу, чтобы какая-то чудовищная линейка была, может быть, клеточки бы. Или что? Положение ставится стороны. А, свой, может быть. Нет, это мы скрыли все. Что? Сюда нажать. Это надо, чтобы наполнить экран. Вот. Нет, конечно, все. Так, сейчас. Нет, это рисовал. Ну, вот, о, смотри, есть, больше треугольники. Да,
Пазл не хотели?
Пазл мы не хотели пока что, да, но в принципе можно. Так, ой. Почему нет? Где она? Это был журнал, да? Значит, информация была настройка шаблона страницы.
Будет применены к новым страницам.
Вот применены к новым страницам. Так, и когда надо сделано? Да.
Нет.
Так, нет. А, это что я сделал?
Это ты что-то сделал. Сейчас.
Ну, если просто файл.
Нет, вряд ли сюда. Должен сказать,
Создать.
Во.
Клеточка.
Да.
Это уже вектор координат. Не уместится электронное хранение, а что увеличить? Нет, сейчас. Страницу не хочу.
Вот.
О, нормально.
Да, сейчас. А проматывать тут вниз? Просто пальцы.
Нет, проматывать тут справа ползунок.
Да, ну пальцем тоже получается.
Ладно, хорошо.
Нет, пальцем там может.
Хорошо, ладно. Разобрались с этими вращениями.
Да, ладно. Ну, хорошо. Well, my first question will be, is there anyone in the audience who does not understand spoken Russian? Okay, so in English then. Right, so this is the symmetric functions course, and well, we're going to speak about some combinatorial aspects of symmetric functions, as the title suggests. So, well, these things we're going to study are applicable in like many places, like representation theory or algebraic geometry or wherever, but we are not going to cover any of that. We're mostly will be focused on combinatorics, and well, this is our intentional decision, so that well, to make the prerequisite for this class as well minimal. So Yeah, so what I'm usually starting with this class with is the following like high school or maybe intermediate school problem. Just tell me how to solve it. Well, so let's take a quadratic equation. X squared plus b x plus q is 0. Is there any way to make it thicker? Вы что, знаете, как это толще сделать, маркер?
Мне кажется, вот здесь есть парный процент.
Правее.
Да,
Правее?
Не, вот
Еще
это.
правее.
Еще правее.
Да, вот здесь.
Да. Нет, это мало. Это, а еще? Так, сейчас. Ой, нет, это не то. Что, совсем нельзя вот так вот? Жирный. Какой-то не особо жирный.
Лично что?
Не хочу, не знаю.
Клетки будут, ладно. Нельзя.
Клетки будут огромные. Так лучше. Okay, so we take a quadratic equation and well, you can find its roots x1, x2. This is even thinner. Okay, let's leave it like this. I think next time I'll ask for normal top blackboard. Hey. Well, let's take the roots of this quadratic equation. X1 and x2 roots. And, well, I can plug some concrete P and Q here if you wish. So, my question is how to find, well, let's say 1 over x1 squared plus 1 over x2 squared. What are you going to do if I ask you to find this? Это вообще видно? Can you see it or? Kind of. Okay. Okay, anyway. So what are you going to do if I ask you to find 1 over x squared, x1 squared plus 1 over x2 squared? Any suggestions? Можно отвечать по-русски. Вопросы можно задавать, можно там, или когда я задаю вопросы, можно на них отвечать на любом языке, который я знаю. Ну чего? Как такую штуковину найти?
Привести к общему знаменателю, выразить через произведение суммы.
8 класс, да, значит. Okay, so it's yeah, so I think if there are people from the pedagogical program here, are there any, by the way? I think, well, the people who are teaching school children are really familiar with this trick. So it's like 1 squared plus x2 squared, right? So, and this thing, well, what are you going to do with this? Well, we know the Viet theorem. So it says that x1 plus x2 is negative b, and x1, x2 is q. So this thing in the denominator is q squared, and the thing in the numerator is, well, you can express it using x1 plus x2 and their product. So I can write that this is x1 plus x2 squared minus twice x1, x2. So this is something like b squared minus 2q over q squared. So, and of course it's much better than, I don't know, finding roots using the explicit formula, taking the squares, taking the inverses, adding them up, making a couple of mistakes. So, well, yeah, so you'll get some expressions with roots, they're terrible. You really don't want to do this. So, maybe red will do better. Красным лучше писать или хуже?
Можно просто толще писать?
А вот, я не знаю, если вы выйдете и поможете мне с настройкой этой доски, я просто, я не знаю, как можно... А?
Там есть левее, вместе настраивать толще тоньше.
Вот что это за звездочка такая? Это средняя, не знаю, она тоньше. Так, сейчас. Ну, все-таки перо. Сейчас. Параметры пера. Во. Параметры пера, может быть сюда.
На треугольник справа скорее.
Так. Очень жирный. Можно вот очень жирный. Kind of better. А нет никакого очень жирного.
Нет маркер используют.
Что? Маркер, он будет прозрачный, ну его к черту. Так, стандартный. Okay, I think that's the best we can have. Sorry.
Клеточки убрать.
Может клеточки убрать? Давай клеточки уберем. А, я не знаю, можно их убрать тут? Так, сейчас. А вот я узнал, что увеличить масштаб это не помогает. Почему?
Нет, она не помогала, кажется, потому что он...
Если так.
Ну, лучше.
It's kind of better, right? Well, anyway, we can maybe erase everything and start from the empty page, right? Так, нет, не сохранить. Okay, so start from scratch. Right, so, yeah, well, this was just a little warm-up problem, and while we were solving it, we were using the fact that the expression we were interested in was symmetric in x1 and x2. So you can express it by the sum of x's and their product. So of course this is true not only for two variables but for arbitrarily many. So what does well, what are the right analogs of sum and the product, and what are the analogs of what is the analog of this statement? Well, I think you know this from your undergraduate algebra class. So let's start. So let's start with the definition of symmetric polynomials. Все-таки он очень жирный или очень жирный, хорошо. So let's take a ring of polynomials in, let's say, and variables. Well, I'll take the ring with integer coefficients. Well, sometimes I'll be using a ring over any field of characteristic 0. Well, but for our purposes, well, Q will do. Or so sometimes we're going to use Q x1 xn, but doing things over Z is like more interesting. And well, but sometimes more tricky. So what are you going to do with this ring? You have a symmetric group acting on this ring by permuting variables. So Sn acts on this ring. Sigma applied to f of x1, so Xn is f x sigma of 1 x sigma of n. So you just act by permuting variables, and well, there are some very nice polynomials which are stable under every permutation. Or if you need to check this, you can check that they are stable with respect to any transposition of two variables, of course, because Sn is generated by transpositions. So, definition is f is said to be symmetric if sigma applied to f is f for any sigma. Or equivalently, f of x1, etc. xn is f of xi plus 1, xi. So you can permute, if you permute any two variables, or just two neighboring variables for any I, and if you get the same polynomial, then this thing is symmetric. For any I from 1 to n minus 1, right? Okay, so these polynomials form a subring because the product of two symmetric polynomials is symmetric. The sum is symmetric. Well, this is, of course, this is not an ideal, right? Well, it has 1 inside. Okay, so I'll denote it as follows. Just the ring of invariance of Sn, or sometimes, well, or more often, I will denote it by lambda n. Okay, and this is subring of symmetric polynomials. Как вы говорите, листать какой тут?
Ну, вот эти вот.
Так, все, что-то нажал, все исчезло. Справа вот этот ползунок, да? Ага. Так. Okay. Right, so, well, let's give some examples of symmetric polynomials. Well, here's my favorite one. 1. N is symmetric. Constant is symmetric. Right. Or you can take the sum of all variables, or the product of all variables. x1 plus xn, or sum of, I don't know, of k powers. For any k greater than 0, 1. Okay, let's say 1. By the way, these guys are called Newton power sums, and we'll see them many times. Or you can take, well, as I mentioned, product of all the variables. one more thing you can do is you can take, well, for instance, you can take any k, any degree k, and take all the monomials of this degree. So let's call it hk. This is the sum of all monomials of degree k. So x I1, x I2, etc. x I k for xi must be xin here, right? xik, of course. And these indices are between 1 and n. By the way, how many monomials are here in this sum? Сколько таких мономов разных степеней k от n букв? That's a killer question. Because nobody, literally, well, I did this experiment many times, and it's really very, very rare to hear the right answer from the first try. And today is not an exception. so you're saying this is n plus k choose, well, minus 1 upstairs. Right, this is right. Why is it so? Yeah, this is usually called balls and boxes construction. Шарики по ящикам. All this. You probably know this from, I don't know, from kindergarten. Suppose you have, I don't know, k apple, suppose you have, k apples and n boxes. You want to put k identical apples into n boxes numbered from 1 to n. So well, let's say n is equal to 4. So in this example, I have 6 apples and n boxes, and and to this arrangement of boxes, I can assign a monomial x1 squared because there are 2 apples in this box, x2 to the first power, then no apples here, so there will be no x3 in this monomial, and x4 cubed. Right, so any arrangement of apples gives you a monomial and vice versa. So this is a bijection, and how to compute the number of such ways to put 6 apples into 4 boxes. Well, you need to replace boxes by walls separating 2 neighboring boxes. So you replace this construction by something like apple, apple, wall, apple. And we don't count the first and the last walls. So apple, apple, wall, then apple, wall, another wall here, 3 apples. So you have 9 objects altogether, and k of them are apples and n minus 1 of them are walls. So you have n plus k minus 1, choose k. You need to say which of your n minus n plus k minus 1 places are occupied by apples, and the remaining will be occupied by walls. So this gives you such an arrangement. And so if you compute the number of monomials of this symmetric polynomial hk, you'll get, well, this number, or alternatively, I really like this this sort of duality. So that, do you know that this is plus or minus negative, and choose k. Do you know this? So actually you can write binomial coefficients for, well, and choose k for arbitrary and not necessarily integer, positive integer. Well, and that's actually what Newton did when he was writing the Newton's binomial. The binomial formula in like 1 plus x to the power n is, of course, it's not due to Newton. It's much older, and well, but Newton was interested in writing down power series for something like square root of 1 plus x. So, or, well, any 1 plus x to any power, and he knew this formula. Well, what we call the Taylor expansion, the Taylor series of 1 plus x to the power alpha. And there are binomial coefficients arising there, so, well, this is a sidebar note about so sidebar. Такое замечание на полях, да? Sidebar about alpha, choose k. What is alpha? Choose k. This is, well, you know what is n choose k, right? So this is n times n minus 1 times etc. There must be k factors here. So the last one will be k, n minus k plus 1. And you divided by k factorial. So if you replace n by an arbitrary, well, complex number alpha, this will still make sense. So this is alpha minus 1, etc. Alpha minus k plus 1. Over k factorial. And what happens if you take alpha to be a negative integer? So let's say n is greater than 0, and you're taking n minus n, choose k. So this is minus n times minus n minus 1 minus n minus 2, etc., minus n minus k plus 1 divided by k factorial, right? So if we get rid of the minuses here in the numerator, then we get minus 1 to the power k, n times n plus 1, n plus k minus 1 over k factorial. And you see that the numerator is exactly what we had here, right? So this is negative 1 to the power k, n plus k minus 1, choose k. So binomial coefficients count the ways to choose k objects out of n without repetitions, and their negative counterparts count the ways of picking k objects with repetitions, right? So when you can take these guys with multiplicities. So, well, end of sidebar. Right, so yeah, we were speaking about this polynomial, hk, and one more thing we'll need is, well, what if we take all square free monomials? So all monomials which have at most one occurrence of any xi. So what if we take the analog of n choose k, right? So the sophisticated version of n choose k. Sophisticated version of a generic function, something like that. So ek, let's take xi1 times xik, where I1 is strictly less than I2 and ik, and these guys are from 1 to n. So I can say that these are square free monomials. And if you evaluate this at 1, you'll get n choose k, just the normal binomial coefficient. And, well, these guys are kind of familiar to us because, well, they appear in the Viet theorem. So, what does this theorem say? That so if you take something like t minus x1, t minus xn, this thing will be equal to t to the power n minus x1 plus etc. plus xn t to the power n minus 1 plus etc. plus negative 1 to the power n x1 xn. So the coefficients of here arising here are exactly these guys, right? So these are this is sum of t to the power n minus k times negative 1 to the power k times ek of x1 xn. Right, so these guys are called the elementary symmetric polynomials. And the HKs are called complete symmetric polynomials. Полные симметрические, конечно. And they're, in a sense, they're due, and we'll see this in today's lecture, maybe next time. So, right. Well, I want to get rid of these minuses here, and this n minus k also looks somewhat ugly. So I'm going to rewrite my Viet theorem in a different form. I'll say that 1 plus x1t etc. 1 plus x and t is equal to the sum of what? Of ek times t to the power k for k running from 0 to n. Right, so there is no minus here, no n minus k here, so this looks much better. And actually, if I wish, I can replace this n by infinity just by saying that ENs are 0 for any, well, EKs are 0 for any k greater than n. So I can say that EK is 0 for any k greater than n. Why is it so? Well, because there are no square-free monomials of degree greater than k. Well, this is like pigeonhole principle, принцип Dirichlet. Well, and so I can replace this n maybe by infinity. Okay. Right, and I wonder if I can write down the same similar expression for hk. So what is? So yeah, I'll denote this thing by e of t, capital E. This will be my generating function for EKs. I'll just put them all together as a series. Well, as a polynomial. A polynomial is also series, right? So, so let's say h of t is hk times t to the power k. My question is whether you can write down a similar product expression for this series. Well, this is an honest series, right? Because k runs from 0 to infinity. Yeah, and I didn't mention that. Well, we say that E0 is H0 is 1. Just put it formally if you wish. Какой черт зрения? Чего? So, any suggestions? What is this guy equal to? Well, here I take the product of 1 plus x1t. So this means that from any bracket I can take either xi or 1. Right. So, well, this means that here in principle I have 2 to the power n different monomials, different choices. If I expand this, and well, corresponding to 2 possible choices for any bracket. And the thing is that, well, if I want the same expression for hk, well, I need to say that I would like to take any xi, not necessarily once, but possibly twice or 1,000 times, as many as I wish.
Может быть, сумма в n степени?
Сумма в n степени иксов, да? Ну и t еще там надо не забыть. Okay, so if I take the following product,
Зеленая страничка с плюсом. Можно ногу.
Чего? Погоди,
Зеленая страница.
в середине странички с плюсом вот это.
Сюда. Вот, на странице.
Погоди, я еще на предыдущий хотел что-то написать. Это противоречит? Она как бы, она это самое, она не бесконечная или что?
Она не бесконечная, она страница.
Она по страницам.
Безопасно нравится.
Так. Okay. So, what I'd like to write here is 1 plus x1t plus x2 x1 squared t squared plus x1 cubed t cubed, etc. Right? Times, well, the same expression for any xi. 1 plus x and t plus x n squared, t squared plus etc. Right, so this is the product of n sums of geometric progressions. And, well, I can find the sum of a geometric progression with such a denominator, xi times t. So this is product for I from 1 to n, 1 over 1 minus xi t. And that's my expression for h of t. Calculation. Is it clear? Пока все понятно? Right. And, okay, but why do we care about these EKs, HKs? Well, actually what we're, well, the reason they're important is the well-known theorem from Algebra 1 course, so fundamental theorem of symmetric polynomials. For any f in lambda n, for any symmetric polynomial, f can be expressed as a polynomial in e1, e2, etc. And such an expression is unique, can be uniquely expressed as a polynomial in E1, etc., En. So what do I mean? I mean that this is not one, this is just a common. So I mean that for any f xn, there exists another polynomial in all the variables, let's say g in the variables y1, yn, such that if I plug in the e's instead of y's, and my e's are polynomials in x's, I get a polynomial in x, right? Such that g of e1, etc., en is equal to f of x1, xn, and such a g is unique. Okay, so, well, I'm not going to prove this theorem. I guess you you heard of this proof some time ago, or well, you can look it up in any algebra textbook. So, well, there are several ways to prove it, but I think if you would like to invent a proof, well, you'll do some kind of inductive procedure to express this, well, some parts of this symmetric polynomial as monomials in E's, and do some induction. So, well, introduce some lexicographic ordering, do things like that. Okay, I'm not going to focus on this right now, but what does it tell us? Well, if let's say in abstract algebra terms, we can say that the ring of symmetric polynomials is, well, looks the same as a ring of polynomials in n variables, right? So, and this, so lambda n is isomorphic to the ring of polynomials in n variables. And this isomorphism is given by saying that yi goes into ei. Okay, but and this is kind of fun, right? Because when invariant ring is, well, you would like to say something about this invariant ring. Well, and it turns out to be a polynomial ring. But, well, you can say that it's not really a ring of polynomials. It has some strange grading, right? So I can say that the ring of polynomials is graded. There is such thing as a degree of a monomial. So let's say something about grading. That z of x1 xn is graded, and lambda n is a graded subring. What do I mean by graded subring? This is the following thing, that if I have a symmetric polynomial consisting of monomials of various degrees, so it splits into parts of degree 0, 1, 2, etc. My claim is that each part will be symmetric in its own right. So every homogeneous, let's say, component of a symmetric polynomial is symmetric. This is not absolutely obvious. This is sort of a statement. So I think I'll leave it as an exercise. Prove that every homogeneous component of a symmetric polynomial is again symmetric. So, well, once you prove it, it simplifies your life, because, well, you can, instead of dealing with arbitrary symmetric polynomials, you can deal with homogeneous ones. Right? Okay, so this is an isomorphism of graded rings if you assign the grading as follows. If you say that yi has degree I. So let's say degree of yi is I. This is an isomorphism of graded ring. Of graded rings. Okay, and yeah, so well, what does the fundamental theorem say is that your ring of symmetric polynomials is a ring of polynomials in several variables with some carefully chosen gradient. Well, let me say that this is not always, such a statement is really something quite rare, I would say. So let me give an example of, a bad example when there is a finite group acting on a ring of polynomials, and the ring of invariants is not a ring of polynomials anymore. So let's say bad example. This example will be really simple. Well, to simplify it, let me take a ring over a field. So let's say, I don't know, C of x1, x2, ring of polynomials in two variables. And I have a group Z2 acting on it. Z mod 2Z acts on it as follows. It changes signs of x1 and x2. X1 goes to negative x1, x2 goes to negative x2. So, I'm sorry, negative. Okay, tell me what are the invariants of this ring. Какие варианты такого действия? What are the invariants of this action? So, C of x1, x2 to the power of z over 2z. What are the invariants? Какие варианты будут? Кто остается на месте под этим действием? That's right. These are polynomials of even degree. So and well, if you want to consider, well, this is a ring, but this is not a ring of polynomials. Well, you can say that it is generated by x1 squared, xy, y squared, and this xy that spoils everything. So there is no way to generate it by two gadgets. So you can say that this is generated by three variables. Let's say y, u, v, and w, modulo the relation like u, w is v squared, right? By the way, what variety does this equation define? Что это за множество точек? Yeah, that's right. This is a quadratic cone. So this is the ring of functions on a quadratic cone. Ring of polynomial functions. And this ring, well, this is a ring of functions on a plane, on an n-dimensional affine space. So you can say that if you factorize, if you mod out the plane by the action of the symmetric group, you get the plane again. And if you mod out the plane by this action, by the central symmetry, you get a code. Well, you see that? Well, it's pretty clear that if you take a sheet of paper, and if you, let's think it's made of not of paper, but of rubber. It's rubber. It will be 0, and well, you can identify the symmetric points. So this means that you kind of fold it twice to make the symmetric points coincide. Well, you see this. So this is indeed a code, right? So, and this point is bad. It has a singularity. So this ring is not a ring of polynomials anymore. Well, so the punchline here is that this situation is really nice. It's, well, as opposed to what you usually have in, well, what you can have with an arbitrary finite group action and a ring of its invariants. Okay. Right, and okay, so we see that the ring of symmetric polynomials is generated by these keys. And if you modify the proof slightly, you can, well, let me also leave it as an exercise. You can say that it's generated by the h's. So, let's say theorem, fundamental theorem prime. The ring of symmetric polynomials is generated by the complete symmetric functions h1, etc., hn. Well, not all of them, because there are infinitely many of them, but well, the first n are not. Okay, and to prove this theorem, well, you can mimic you can look up in the textbook for your favorite proof of the fundamental theorem itself and adapt it somehow. But that's not what we're going to do. We'll use the generating functions instead. So, proof. Well, in there. Да, впишите, пожалуйста, номер курса. Please write down which year are you in, like bachelor, master, bachelor, third year, master's, second year, whatever. Okay, so let's recall that E of t is the product of 1 plus xi times t, I from 1 to n, and h of t is the product also from 1 to n, 1 over 1 minus h by t. And you see these guys look almost as inverses to each other. Well, the thing that that we need to correct is this sign here. Well, so let's say that if we plug in negative t instead of t, we'll get series which will be which will be inverse of each other. So e of t h of negative t is 1. Right. So this is a functional equation of these generating functions. All right. And this is an equality of two formal power series in T. See that? Well, this thing here is, I can tell you that this thing is also a formal power series in T. Well, except that almost all its coefficients are 0. But, well, it's a power series in its own way. So, well, we can say that sum of ek t to the power k times negative 1 to the power k hk t to the power k is 1. And let me let me expand this. This is k greater than 0, greater than or equal to 0, and this is also 4. All right. So let me write a couple of first coefficients of this equation, of this equality of two power series. Well, the first one is E naught times H naught is 1. Well, that's not a great deal because we know that both of these guys are 1s. Okay. What else do we have? We have E1 minus H1 is 0. E2 minus E1 H1 plus H2 is 0. This is a coefficient in front of t squared in this series. This is really a bad idea to scroll it like this. Well, here we are. So E3 minus E2 H1 plus E1 H2 minus H3 is 0, right? So this gives you a system of equations. Well, I would say like infinitely many of them, countably many. Да, допишись там курс, кто еще не писал. And this is like a triangular system of equations. So out of this system, I can find, well, knowing E's, I can find H's one by one. Like H1 is equal to E1. Well, all monomials of degree 1 are the same as square monomials of degree 1. Fair enough. What else? So if we are interested in H2, we can say that H2 does it want to scroll, I wonder? So H2 is E1 H1 minus E2, and this is like E1 squared minus minus E2. Or you can find the third one, H3 and H3 is, well, E3 minus E2 E1 plus E1 H2, and we know the H2 already. So this is E1 squared minus E2. So this is something like E3 minus twice E1 E2 plus E1 to the third. So my question is, what will the next coefficients look like? So but my next question is, what if if I know the E's, I can express the H's, right? My question is, if I'm doing it other way around, if I know the H's and I want to express E's, can you tell me what will be the formulas? So, how to express E1? Well, E1 will be H1. E2 will be equal to E1 to H1 E1, which is H1 squared, minus H2. E3 will be equal to what? H3 minus twice H1 H2 plus H1 to the third. We see some kind of similarity, right? Скажите, почему так? Кажется.
Потому что симметричные получается.
Yeah, that's right. The system of equations we had upstairs, upstairs means upstairs. Yes. Делать, сколько они это делают вообще? Ну, в принципе. О, отлично. Now, so that's the system of equations I was looking at, and it is indeed symmetric with respect to replacing H by E. So you see that the formulas you get for expressing H's via E's are the same ones as those you get for expressing E's via H's, right? So the moral of the story is that if you know the H's, you can express the E's and then refer to the fundamental theorem. Say that anything is can be expressed via E's, and the E's can be expressed through H's. And other way around, well, the uniqueness statement is also kind of free, right? Because if you have an expression in H's which is equal to 0, then this gives you an equation, an expression in E's, and this must be 0 as well. So this implies the fundamental theorem for the fundamental theorem prime, as we called it, the fundamental theorem of for complete symmetric functions. All right, so we can say that this ring of symmetric polynomials is algebraically generated by the H's. So lambda n is z of E1 En, and it's z of H1, etc. Hn. Right. So, well, algebraically as a ring. So, if you want to have a basis of with this as an abelian group, you can say that, well, we can take any monomial, or we can take all the monomials in E's or any monomials in H's, and say that all possible products of E, let's say, lambda 1, E lambda 2, etc., E lambda K, generate lambda n as an abelian group, as a free abelian group. Or if, as a free abelian group, if you replace Z by field K, you'll see that these guys generate lambda n as a vector space. So it's nice to have a basis of a vector space. All right. So and what are lambdas? Well, I can say that lambda is a partition. That lambda 1 is greater or equal to lambda 2, etc. to lambda K. And these are positive integers not exceeding n, right? Because I have n variables, right? Okay, and I can also say the same thing about h lambda 1, etc. h lambda k. So the basis is indexed by partitions, right? And it's a nice thing, but partitions are a very nice combinatorial object, right? And well, so we have a basis of this ring, but actually, you can say that there was a simpler way to do that. If you want a basis of this ring, well, you can just say that polynomials are generated by monomials. So this is the most natural basis of this ring ever. And if you want to generate symmetric polynomials, you may want just to symmetrize monomials, right? So, simpler way. Symmetrize monomials. So, if we have some monomial x 1 to the power lambda 1, etc., x n to the power lambda n. Let's take its symmetrization. This is the following thing. Well, let me commute all the x's in any way I want. So x1, let's say sigma 1, lambda 1, etc., x sigma n lambda n, and take the sum over the symmetric group. And what I'm going to have will be a symmetric polynomial, right? But, well, I would like, well, all the coefficients of this polynomial will be identical, right? Will be equal. But I would like to make them equal to 1. So let me divide it by some constant in such a way that all the coefficients are equal to 1. But 1 is equal. All coefficients are equal to 1. Well, let me maybe say why do I need this? Suppose I have 2 variables and I take a monomial x1, x2. So if I symmetrize it, I need to sum up over the group of permutations, it will be twice x1 is 2. And because I want to do things over z, not over a field, I would like to have x1 is 2 instead. Right? This is 1 over 2. So the symmetrization of a symmetric polynomial is itself, as the polynomial itself, right? Okay. So, and let me say that if I'm starting with the sequence lambda with 2 sequences, and one of them is obtained from the other by permutation, I'll get the same polynomial, right? So I can say here that my lambdas are ordered in the way I want it. So let me say that these lambdas are ordered like this. And, well, let me call this thing m lambda. And this will be called a monomial symmetric function. And, well, it's pretty clear that these guys also form a basis of lambda n. And lambda form a basis of lambda n. And, well, but you see the difference here. It's also used by partitions, but these partitions have at most n parts, while for the e's and h's, they had arbitrarily many parts, but these parts were not exceeding n. So these things are conjugate in a sense. So the punchline here is that we have, for the moment, we have 3 bases of lambda n. These are e lambdas. Well, yeah, we denote e lambda 1, etc. e lambda k by e lambda for sure. So e lambda, h lambda, and m lambda. And I think that's, well, next time we'll define our favorite basis of sure polynomials, which will be also symmetric and which will have very nice properties. But well, that's it for the moment, and well, let's make a 10-minute break now. Let's see what else is our class. Also here in 10 minutes. Можно писать задачки, да?
Чуть зажми, может, не учусь. Okay. So, let's start, I think. Sorry for my English, it's a little bit rusty. Maybe if maybe I will switch to Russian if it will be too difficult for me. Okay, so we have 3 families of bases. Elementary, symmetric polynomials, complete symmetric polynomials, And monomials, not functions, lambda, which are results of symmetrization of monomials. And they all are indexed by partitions. Partitions are just sequences of ordered infinite. So we will discuss how these families are connected with each other. But let's start with some exercise about generating functions. How to express this product via elementary symmetric monomials. So it's a symmetric monomial, of course. Have anybody got any ideas how to express it by elementary symmetric functions? How to do it? Как это сделать?
Можно множители разложить и отдельно посмотреть.
Ага, yeah, very good idea. Let's factor this right into linear factors. It can be easily done. Like this. Okay, what's next?
Ну, отдельно посмотреть на произведение первого типа и отдельно произведение второго типа. И выразить через Е, которое мы вводим.
Yeah. This. And
Е от минус
uh-huh.
единицы.
Yeah, these guys are very similar to this guy, to the generating function for elementary symmetric functions. So how it can be done? We factor 2 to the power of n out of our product. Plus times ага.
Чего там?
Да ничего, мы вспоминаем производящие функции. Так. So this guy here is just our generating function evaluated at 1/2. And this guy is our generating function evaluated at -1. So now we just write the definition of our symmetric function.
Я раздавалась?
Раздала.
У всех вторых есть?
So, ой, пластик. Понятно? Как-нибудь его меньше нельзя.
Уменьшить пластик можно, он запутаться.
Да, я возьму свечу. Да, вместо такая. Ну, да. Вот это вот, ты что он стирает кусками. So, this product can be expressed like this. Ну что, раскрывать скобки, наверное, не хотим, да? Я не хочу. Так, окей. And what did we do in the similar exercise where a polynomial cannot be factored into linear factors? What should we do here?
Почему не может? В комплексных может.
Yeah, of course. This guy here can be factored anyway. Just in complex numbers. One plus omega xi. One plus omega conjugate xi, where omega is the cubic root of 1, like this. Of course. And now we do just the same thing as here. I think I will not write it explicitly. Right like this. Okay. So this is how our generating functions work, and we can remember this thing here. Where we used some generating functions to все ползло. Отвратительно.
Очень.
Да.
Очень плохо это сказать.
Да. So we used generating functions and proved this identity that we then used to express e's and h's by each other. Now, let me rewrite, I think, this these equations. Q1 So these equations can be used to express E's via H's, and now let's do this explicitly. Let's solve the system explicitly with Cramer's rule. I think да. Да, я тоже как раз хотела это сказать. So we have the system. We need to write an expression how Hn is expressed via E's. Да нет, плохо, но вернулся. Да. Нет, это тяжелее, это будет вернуться. Трансформация.
Бежать, такую бежать. Ладно, мы знаем.
Ну да.
Правильно, надо забыть. Не сам решай.
Такая система, у вас она так решается. Да. Надеюсь. Первый курс какой-то. Первый курс правила Крамера. Знаешь уже?
Маша, знаете правила Крамера?
На решение системы.
Да,
Определите делить разделить.
да.
Ну, странно.
Ну, не верно с первого курса. В смысле, вроде да, было.
На алгебре было, да? По идее, должно было быть, если
Да.
рассказывать
Должно быть, да.
про определители, про, ну, так сказать, обратную матрицу. По сути, оно и есть.
Ну да.
Если не помню, как пишется Крамер. Через Кей.
Через Си.
Или через Си, наверное.
Там было. Здесь, конечно.
Не, пока оставим
нет?
второй.
Ну ладно. Ну да, да, и да.
Да можно, в принципе, можно по строке в стол разложить.
Можно по индукции. Нет, можно по индукции.
Да.
Все взял,
А, хорошо. Ну, получается, значит, тогда. Прикольно.
Хорошо.
I don't get the question.
Может быть. Let's
So, I'm going to show.
you're on the first one or the second one? Which one is?
So, no, we are solving the function.
Oh yeah. So you need to well, you have this system of equations and solutions. So we need to show this. Попался.
Ну, она устная будет.
Ну, на уж это Крамер или индукция? Не любит никто. Правило Крамера.
Ну, ладно.
Ну, нет, ну, во втором можно по индукции делать, конечно.
Ну, можно, конечно, да. I think let's write this equation in matrix form. Let h's be our variables and e's be our coefficients. So we write it. Write it like this. One. No. Is h's are variables. These are our coefficients. Minus e. Okay. Plus minus now. I don't want to calculate the sign here. No. Minus 1. Minus 2. Minus 3. And here. So I wrote this system in matrix form, and now we use our Cramer's rule to calculate HM. We need to divide two determinants. In denominator, we have the determinant of this matrix, and it is plus or minus 1. power of number 2. And in the numerator we have the determinant of matrix where the last column is replaced by the column of ease. Thanks. And now, if we are careful with the sign, we permutate the columns to put this one here. And then we get exactly what we want. Yeah, we need to be careful with science. I think every one of you can do it yourself. Follow the science correctly.
Well, for the sign, I think it's pretty easy because this sign must be like K. Well, the sign in front of E something, right? So if you're computing HK, then EK is taken with the sign -1 to the power K minus 1, right? So with the opposite sign from, well, you see it from this equations for that. For, say, for H3, this is E3 plus something. And for H2, this is minus E2 plus something. So, yeah, that's an easy way to control yourself. You can figure out from this matrix what should be the sign in front of En, right? Because it's like a diagonal term. Okay.
Yeah. So this how.
So what you need to do is to make an even number of mistakes in this process.
As always.
But for the second one, I think induction is also, well, maybe much easier, actually. So take the row expansion of this determinant and...
Induction also works here. Okay.
Слушай, а есть какой-нибудь в загашнике какой-то пример, когда Крамер работает на индукцию, ну, то есть, когда Крамер прочит индукцию, каких-нибудь таких?
Не знаю.
Тут, по сути дела, тоже индукция,
Да.
конечно.
Ну,
Ну,
знаю.
или опять же то же самое.
у меня в загашнике нет такого примера.
У меня тоже нет вопроса.
Я правильно люблю. Я не включить меньше, но... Окей.
Это про это самое. Я не суду, а как японский кроссовок, да?
Что?
Вот
Это, да. Немножко есть.
Ладно, что, пускай думают.
Ну, я хочу тебе сказать, что здесь происходит.
Где? В третьем?
В третьем.
Давай.
Да. So, the third exercise is about another family of generators in the ring of slot functions, like polynomials. And these guys are so-called Newton power cells. The first one is just the same. The second one is the sum of squares. And the nth one is the sum of x powers. It can be proved that every symmetric polynomial can be expressed by these guys in similar way as we prove that every symmetric polynomial can be expressed by elementary symmetric polynomials, but we will do it another way. We will try to express elementary symmetric polynomials by this guy. And the third exercise is just about.
Well, just one remark about these Newton polynomials.
Ну, да, ну, я бы
можно?
сказала, да.
А ты сказала, да?
Нет, я бы сказала, но потом немножко про то, что там не целый Да, ну.
Okay, so in a sense, these guys are worse than the e's and h's and the monomial functions because they do not generate the lambda n, which is the ring of symmetric polynomials with integer coefficients, right? So this is not generated by P1, Pn. What is true that if you take rational coefficients, this will be fine. So lambda n, I'll put tensor cube here. So ring of polynomials with rational coefficients is equal to isomorphic to z cubes. Well, even for n equal to 2, you see that if you want to express x1, x2 by the Newton power sums, you need to take x1 plus x2 squared minus the sum of squares divided by 2. So you see that this is 1/2 of b1 squared minus b2. So we need to have, well, this 1/2 here. So, but yeah, these guys are also pretty important. We'll deal with them later. And yeah, the part A of this problem is it shows the following principle that if you have a product like xi t, what do you do when you see a product? Well, like products are bad, sums are good. What do you need to take to make a product into a sum? You just take a logarithm, right? And the logarithm derivative, well, I think you know the formula. Okay, so enough said. Как интересно сохранить все. Да хрен знает, может не надо сохранить. Нет, ну записки лекции.
Нет, вы знаете, такого ведь не надо. У нас есть нормальный На русском, правда.
На русском и по-английски, потому что. Все-таки в режиме реального времени не буду перепиливать на английский. А то он все-таки вот. После завтра. 6 часов несет, вот другое. Больной головой, бессонные ночи. Делать ничего. Ничего не делать. Тюк-тюк. Взять кофе, кого-то дорогой. Ну, можно сделать какой-нибудь чат, мне кажется, да. Знаешь, что? Не исключено. Сейчас. Правильно. Да, пусть, да. Сейчас. Legal control. Нет, это просто это все нажимается. Я думаю, что вот,
Он делает код, просто люди на телефоне показать, сканируют. Потом прибавляют уже.
Или я в description добавлю, потому что это типа свет.
У кого есть Telegram, может открыть на телефоне. Если его превыше. Просто сканировать. Она может пройти через фото?
Нет, я сделал.
You just scan the You just scan. Снова складывается.
Just turn the camera.
Ну, больше людей.
Я тут какой-то сейчас
Ну, если будут еще желающие, как-нибудь тоже добавьте их туда. Сейчас я могу строечку можно было. Всем можно было делать дополнительные ссылки.
человек. У нас кого-то не хватает.
Ну ладно.
Делай.
Ну, да, сейчас пока мы разбирались с чатом. Кто-нибудь уже посчитал со степенными суммами? Have anybody done something about power sums? Что так? Ну ладно.
Без утра.
Ну, уже
Уже
12, но
пора потихоньку забраться.
уже 12, но мы не отвечаем на тех, кто не ставится. Ну, нет, получилось, что логическое производное.
Логарифмическое производное.
Да, семечко логарифм получает произведение в сумму. Для производной от суммы сильно симпатичные. Можно вот в таком виде, когда ты пишешь его как сумму. Потому что брать производное произведение, а можно можно производного логарифма, а можно сначала говорить по этой штуке, а потом где-то мы производную. Ну, это наш да? Надо делать то, что приятно. Производное произведение неприятно. Ну, сейчас. Может, сейчас нет. Может быть, да. Да, там может быть какая-то ошибка со знаком. There can be some mistakes with signs. Может быть, есть. Ой, да. Сейчас. Сейчас нет. Это оно с плюсом. Нет, потом просто то, что раскладываем. Первая единичка все равно. Один минус квадрат. Товарищ. Да? Получается. Логическое производное можно сначала говорить заменили, а потом взяли производное. А можно взять, что как производную любого алгоритма. Вот есть штрих делить на один. Видишь, что удобнее делать тогда, как сумма записана. Это да, да, ну С, она что-то то же самое.
Ну, из Б.
Да, ну из Б.
Как-то так сразу.
Ну да.
А Б, надо вот так сделать. Там что-то получится.
И все получится. Ну, отлично.
Я сначала подал через вот это, но потом понял, что... Ну, в общем, это можно давать какую-то информацию, посмотреть на то, что написано. На решение.
Сейчас, а может, это не так, что так не очень просто.
Ну,
Да, если кто долго думал.
Вот я написал вот в таком виде. Ну, то есть, ну, типа, вот это, по сути, я видел отдельно. Вот. Теперь вот здесь вот можно посмотреть. Вот здесь вот видите все вот эти вот, потому что, ну, типа, можно убрать одну штуку отсюда, любую технику, любую скажем.
Да, да, тут человек напрямую просит Ньютона.
Нет,
Да, то есть...
в принципе, можно.
Да,
Да.
можно, мне
Нет, ну,
интересно.
на самом деле, вот это как бы упаковывает все рассуждения в производящие функции хороши тем, что они вот все это упаковывают в
Да.
одно, да. Это, конечно, можно и без.
То есть, что
Это как бы те же самые манипуляции средами.
здесь каждое это там выделенные мы решаем без квадратов степени k. Вот. Здесь это у нас решение без квадрата степени k-1 умножить на сумму xn. Соответственно, здесь каждый получается k раз, потому что нужно так. Вот. Потому что правильно. Ну, можно убрать одну штуку, получится что-то отсюда. Вот. Почему все остальное здесь сокращается? Ну, потому что у нас есть любые решения, там, умноженные, это, короче говоря, там только в одном члене может быть степень больше единицы. Вот. Соответственно, оно может получиться два раза. Одно это когда мы когда там было, другое когда не было. Вот.
Ну, хорошо. Это проще.
Да, это правда.
Что, разберем, что происходит? Или хотите еще подумать? Решение было есть. Окей.
А кто такой лямбда штрих?
Сопряженное разбиение. Если вы представите как диаграмму Юнга, вот оно отражается в диагонали. Ну, поговорим. Так. Окей. This is our generic function. So when we take a logarithm of this guy, it becomes the sum of logarithms. And now take derivative of this logarithm. Derivatives of logarithms. Derivative of this guy divided by this guy itself. And now we express express this thing as a sum of geometric progression. Xi minus xi squared plus t xi cubed squared. And this is exactly now we regroup this thing and get exactly what we want. Не так, конечно. get generating function for our power sums. It's the power of k minus 1. So the logarithmic derivative of e is generating function for p's. Okay, but there's another way how we can calculate our logarithmic derivative. It's the derivative of e divided by e. Now, if we write that the derivative of this generated function is a product of our generated functions, we get exactly the equation in 3b. Like we've done here. Here we write an equation for these two generating functions. And here we write an equation for these generating functions. And then we have exactly this equation that helps us express e's and p's via each other. Okay, and 3c can be done exactly as the exercise number 2, Cramer's rule or induction. And so we prove that e's can be expressed via p's, and so p's generate the ring of symmetric polynomials with rational coefficients. Окей. Вопросы по этому месту? Окей. Давайте еще вот что напишем. Напишем, что polynomials P lambda, which are, of course, the product of is indexed by partitions. They form a basis of our ring. So now we have here we had 3 bases, and now we learned about the 4th one, which is basis of Okay. So there are these three bases, and the question is how these guys can be expressed via this guy. What is our transition matrix here between this and this, or this and this? And the fourth and the fifth exercises are about this. Okay. So it states that if lambda is a partition with three parts, and mu is a partition with n parts, where n is the number of variables in lambda can be expressed что удалось тоже. So we express is via m's, and the coefficient here is the number matrices with k rows and n columns with entries 0 and 1, like this, such that the row sums are lambdas and column sums are mus. Think about it a bit, and then we will discuss.
А там знак меньше, это в смысле лексикографический или даже
И так можно понимать. 24 лексикографические. Да, вообще. Оно во всех смыслах меньше. И в дискографическом, и в смысле доминирования. Ну, в общем, можно. Да. Что вам происходит, понятно, или как не очень?
Понятно.
Привет. Чего, как успеть?
Ну, да.
Про это самое, про японские кроссворды.
Да. Не совсем, они просмотрены про размер блока.
Да, не, ну, ну, это как, это знаешь, как, не знаю, рентгеновский снимок. Ну, что такое рентгеновский снимок? У тебя есть там трехмерная картинка, кости. Да, и ты, значит, ты смотришь плотность по каждой прямой, да, и, значит, задача по этим плотностям вдоль каждой прямой установить картинку. Ну, вот это такой дискретный рентгеновский снимок.
Просто уже берем вот и так. Забей, вот. Забей, вот. Да, вот.
Да. Что же тогда делать стандартный?
Не знаю. Можно проверить. Он как-то хуже.
Нет.
Да, он какими-то частями это все стирает.
Интегрирование по частям бывает.
Вот еще и тут можно. Он может писать текстуром.
Да.
Тоже. Да, не пластик тебя. Что-то вот они сделали.
Да, а более толстые они не сделали.
Да. Мне кажется, это можно сделать более толстым, мы не умеем. Ты не будешь, ты не будешь.
Ты что-то уже говорила про это?
Нет, я пока ничего не говорила. Я хочу матрицу из иксов написать, чтобы... Мне кажется, как-то можно сделать сплошную страницу. Ну ладно. Нет, вряд ли навигация. Нет, это парные, нет, это все не то.
Это не то, это как это все журнал, может быть.
Нет, это...
На старых
Нет, кажется, по странице. Да, оставь. Хочу... Ладно, наверное, даже не буду писать на новой странице, а напишу вот здесь.
Ну, прости.
So you can think about a matrix like this. And zeros and ones here correspond to variables in this matrix which we pick or don't pick. So we pick variables where there are ones, and we don't pick variables where there are zeros. And like this, we will generate a monomial. With this, will make it a little bit easier. Ну, что я сказала, что мы можем выбирать.
Нет, я
Нет,
понял,
да, нет, я ничего не сказала.
Нет, ничего не было.
Да. Ну, вы сказали. Человек пришел, сидит необесточенный.
О, Господи.
Да.
Человек ему для класса а его там сидели.
На самом деле, вы в какой-то степени все услышали, что реакция происходит. Задача правильно будет решать.
Да, рисовать можно. Какие-то самые. Давайте сюда. Ну, то есть можно рисовать, понятно, что нам это конкретно штуку. Ну и так далее. Да.
Слушайте, современное поколение знает, что такое эти самые японские кроссворды? Do you know the nomograms puzzles? They were popular maybe some 15 years ago. Well, there was some picture on grid paper with some boxes highlighted. Something like this. Well, of course, it was usually bigger, and it was some funny picture. And what information you got was the length of blocks. Like, I don't know. Let's make it like this. So here it would be 2. Here it would be 1, 1. It's 4, 1, 2. All right. Block is a sequence of consecutive black boxes, and same for columns. It was like 2, 1, 1, 1, 1, 1, 4. And well, it's sort of like in Sudoku. We need to figure out the exact position of the black puzzle, the black boxes, and usually in the metro you saw people sitting, not staring at at their phones like today, but rather they were working through these books of these puzzles. In Russian they were called Japanese crosswords. And here it's more or less the same, but we get less information. Here we have like sequences of ones, and well, you have a two-dimensional picture, and suppose you have an X-ray, which tells you how many boxes are on each, how many highlighted boxes are on each row and on each column. Like instead of having 1, 1, you get just 2 here. Here you get 2, 3. Right. And so this number is the number of such configurations corresponding to a pair of weights, lambda, weights and sequences, partitions, whatever. Okay. So it turns out that these are coefficients of expansion of E lambda in the monomial basis. And same about H, but here we can put, like, well, the difference between H and E, you know, that for E you can put only one apple inside a box, and for H you can put several apples into a box. And well, this will be the case with these two-dimensional box sets you fill with apples. Right.
У нас очень пар заканчивается.
Пора закончится. Ну, сейчас, когда она закончится? Через 2 минуты закончится.
Сейчас. Сейчас что ли?
А она где сейчас?
Ну ладно,
Друзья,
Да нет, это...
слушай, мы не сказали, какая нам будем speak. Okay, yeah. So we forgot to write or to tell what is the conjugate partition. So if lambda, suppose that lambda corresponds to partition lambda 1, lambda 2, etc. lambda, and I can draw the Young diagram like this. Yeah, we have rows of length lambda 1, lambda 2, etc. So this will be 6, 6, 5, 3, 1. Okay, and what you can what you can do is you can reflect this diagram with respect to this axis, or which is the same, compare the lengths of the columns instead of rows. So this will be mu1, mu2, etc. So in my case, this will be 5, 4, 4, 3, 3, 2. And this is mu, and this is lambda, and such a diagram is called the conjugate partition to lambda. So you replace rows by columns and vice versa. So twice conjugate is, of course, the original partition. So yeah, it turns out that the coefficients mu, lambda, lambda prime is 1. That's 1.4c. Okay, so our time's up. So please have a look at the problems you didn't solve today. Have a look at them at home. And well, I think I'll see you in 2 weeks, but I'm away next week, so Anna will give the next class. Ладно. Ну что, все? Моя очень все, спасибо.
Обед тут сейчас не
Не знаю.
Кто у вас тут обед?
Хотел показать, но всякие лекарства.
У нас сейчас.
У вас сейчас, да.
Да.
А, то есть надо скорее бежать,
Пока-
не добежал два партнера.
Пока не началось.
Да.
Да.
Ладно.
Так, ладно, мы не будем это сохранять. Я выпишу
Да.
в обед, еду в школу.
А я поехал.
Хорошо.
Все, счастливо.
Вот, да, спасибо. Да. Ну, не знаю, да, ну, хорошо. Да, это